Hello everyone. Welcome to this lecture on electromagnetic induction. In today's lecture, we will try to understand the relation between self-induction and mutual induction. If you remember, in the previous lectures, we have talked about what is self-induction, what is mutual induction independently. And in today's lecture, we will try to understand how they are actually related or how exactly we can represent the relation between the self-induction and mutual induction. Now, since already we know that for mutual induction, we at least need two circuits or two different coils, and both the coils they have their own self-induction. So, in this case, let us consider two different coils or circuits C1 and C2 as shown in this figure. So, this is circuit C1, this is circuit C2, and both these circuits are carrying current I1 and I2 respectively. So, and the directions of the current is also as shown in this figure. That means in this particular circuit the current is flowing in this particular direction, so this is I1, and in this particular circuit current is flowing in this direction, that is same direction actually, I2. So we can say that both the circuits are having current in clockwise direction. If it is so, in that case, because of this current I1, there will be a self-induction linked with this particular circuit C1, and similarly because of the current I2, the circuit C2 will have its own self-induction. But because of current I1, there will be an EMF generated in coil 2, and similarly because of the current I2, there will be a EMF generated in coil C1. So this gives rise to the mutual induction or mutual interaction between these two coils. And that is why once I want to calculate the total energy of the system, we have to take into account both the self-induction and the mutual induction. We'll take into account the self-induction of both the coils, that is C1 and C2, and mutual inductions between them. In previous one of the lectures, you must have learned that if L is the self-induction, in that case total work done by current to flow against the back EMF is given by half of L I square. So this is the same expression we are going to use in order to find the total work done. So basically what we are interested in, what is the total energy of the system. So total energy of the system in this case is expressible as half of L1 I1 square, which is the energy stored in the coil 1 because of the current I1, then half of L2 I2 square, which is the self induction, or this is because of the work done or the energy stored because of the self induction of the coil C2 due to the current I2, and because of both the currents and mutual interaction between these two circuits, there will be an extra energy which is given by this expression I1 I2 M. Now how exactly this relation appears or how exactly this expression comes, I will make a separate video to explain this particular thing. For the time being, you just consider this to be true. Alright. So what we have seen, that total energy of a system of two coils carrying current I1 and I2 respectively is given by the energy due to the self-induction of both the coils taken as a summation plus the energy due to the mutual induction of these two coils. Alright. So this is the total expression of the energy. Now, once again I am writing this particular expression. This is the same expression as I have written in the previous slide. Now what I am going to do, I am going to multiply both the sides of this equation by 2. That means I am going to multiply this by 2, and in this side also I am going to multiply it by 2. If I do that, I get twice Wt, then L1 I1 square because these 2 and that 2 gets cancelled, then L2 I2 square, once again these 2 and these 2 gets cancelled, plus this 2 will come over here, twice I1 I2 M. I hope this part is clear. Now in the next step, what I am going to do, I am going to divide both these expressions by L1. So there are a lot of mathematical manipulations are there, and the steps are very important. So you just have to remember these steps in order to find a relation between these two, self-induction and mutual induction. All right. So twice Wt upon L1, if I do that, in this case L1 gets cancelled because I am dividing it by L1. So what remains is I1 square. Then L2 by L1, I2 square plus twice I1 M by L1 into I2. just purposefully I have written this in this fashion, and that purpose will be very clear to you. So in the next line, that implies I1 square plus twice I1 m upon L1 into I2. That means this particular term I have written here. This particular term I have written in the extreme right hand side. All right. So why I have done this? I have done this because here I can see there is a term called twice I1 and I2. This is the only term which carries both these terms as I1 and I2. So I can somehow frame a relation as a plus b whole square or a minus b whole square, whichever is suitable. But it is a plus b because there is a plus sign here. So that is why generally a plus b whole square is equal to a square plus b square plus twice ab. So if I consider this term to be twice ab kind of a term, and this term to be a term, in that case I need to figure out the term b. So how can I figure out the term b? Figure out the term b is nothing but this m upon L1 into I2. This must be the b term. So that is why what I have done in the next step, I have just taken a summation of m upon L1 I2 whole square, but this term was not there initially in this expression, so I have taken a subtraction also. All right. So once I do that, then combination of these particular terms, these three terms, give me a term as I1 plus m upon L1 into I2 whole square. This is quite like a plus b whole square kind of a thing. Okay, this is just a mathematical manipulation. You must understand this particular fact that I am somehow watching this term twice of I1 m upon L1 I2. I have figured out this whole game. All right, so this is a mathematical manipulation. So next what remains is this term and this term. So that is why I have simply written it as L2 by L1 minus m upon L1 whole square. By the way, this is a square term, so m square by L1 square taken a product with I2 square. All right, so I have got already these two terms, and which is equal to twice the total energy stored in the system divided by L1. But L1 is anyway a constant. L1 is nothing but the coefficient of self-inductance of the first coil. L2 is the coefficient of self-inductance of the second coil, and similarly M is the mutual inductance between them. So these are all constant terms. Now this particular term which is on the left hand side, this term must be positive, so which I have discussed in this particular slide. So the left hand side of this equation 1, so let's consider this equation 1 is always positive. Okay, because self induction, this property is positive and total energy saved in the system is also positive, so this term must be positive. Now this is possible only if, how is this possible actually? If this has to be positive, then the right hand side has also to be positive. I mean this term has to be positive, and independently this term should also be positive. So this is anyway a positive term because this is a plus sign and there is no negative sign over here. There is no negative term, so this term as a whole taken a square will also give us a positive term. What about this particular term? There is a negative sign. Now in order to make this particular term, the whole term, positive, we must ensure that this term which is here should be greater than this term. So the left hand side of equation 1 should always be positive, and this is possible only if the second term in the right hand side is positive. Okay, thus we must have L2 by L1 minus m square upon L1 square greater than or equal to 0. Why equal to 0? Because even if it is equal to 0, in that case also you remain with this term only, which is a positive term. So this is also a possibility, because we have to make the left hand side to be positive. I mean, by our principle, the left hand side must be positive because it's an energy term. An energy term must be a positive. There is nothing called negative energy, isn't it? So in this case, the second term on the right hand side must ensure this fact that the left hand side term should be positive. So in order to do so, this first term, that is L2 upon L1, should be greater than or equal to m square by L1 square. That's what I have basically written here. So next step easily follows from this. In that case, I have just considered an equality in the next step. By the way, I have not considered a greater than sign, but I should have actually considered. Please rectify this. This should be greater than sign. So L2 upon L1, that's equal to greater than or equal to m square upon L1 square. So 1 L1 gets cancelled. What you remain with? L1 L2 greater than equal to m square. This is actually the required relationship between self-induction and mutual induction. Alright, so if you have two coils, they are carrying independent current of their own, I1 and I2. They have got coefficient of self-inductance as L1 and L2 respectively. And if capital M be the mutual induction between them, then the relation goes as the product of the self-induction or product of the coefficient of self-inductance between two coils is always greater than or equal to the square of the mutual induction between these coils. So this is a very critical kind of a relation, you can say. It's an inequality. Sometimes it can be an equality. So it's a very interesting relation and very important also, this derivation. So please go through this once. This is very easy. There are some mathematical manipulations. The steps must be remembered. And once you do that, I don't think this will puzzle you much. All right. So that's all basically I had for in this particular relation, in this particular lecture. In the next lecture, I will make a separate video on how exactly to calculate the energy stored due to mutual induction. All right. So thanks for today. Thank you.